Hey, so hi everyone, good evening. I hope you all have a great time. Despite maybe some makeup tutorials, I'm not sure if you have other makeup tutorials from um other like classes. But yeah, let me just check the pre-sentiment check, right? Think yeah. Oh, one student seems very happy, two students very sad, six students just meh. Yeah, because yeah, I think previously for my other makeup tutorial, yeah, it's centered around the lower half, but this one is more on the first half, so I'm happy also. 10 people said that they got assignments. Yeah, me too. One person very excited. I hope you all have this one person, I hope you have a great time for this long weekend. Okay, so without further ado, let's start today's tutorial. So today we are going to talk about the data link layer. So in case that you are comfortable with turning on your camera, that would be great. So I'm just not talking to boxes with names. But yeah, it's fine if you want to turn off also. Yeah. In case of any questions, feel free to just raise your hand or you can ask the question on chat. I'll be checking them frequently. Okay. So today we noticed that inside data link layer, it's actually we have to handle several types of errors also, specifically because when you send data through the link layer, there can be corruption due to collisions, right? So there has to be some form of an error detection also. So the way that we have introduced in the lecture for error detection is by using something called parity checking. So how does this parity checking work? It is similar to checksum, but instead of checksum for every single data, right? We are going to do it just for like small chunks of data. So suppose that here I have this data here. So show why this connecting. Yeah. So suppose this data here we have like 0, 1, 1, 1, 0, 0, 0, 1, 1. So in the lecture, we have been introduced to the scheme called an even parity scheme. So inside the even parity scheme, basically we are only going to add a parity bit of 1 if the current data contains an odd number of ones. So the goal is basically we want to add a parity bit such that the number of ones inside all the data bits with the parity bit is an even number. So say in this case, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 ones inside the data. So we have to add one parity bit such that it becomes 10 ones. So if it's even, then that is basically the even parity scheme. This is introduced in the lecture. Okay, so this is what we call the single bit parity checking, which allows you to detect single bit errors. So suppose that one of them here, for example, this 0 is being changed to 1 instead. Now we know that the data here, we have a total of 11 ones, which says that this is actually incorrect based on the parity scheme. So in case that one bit error is in case of a one bit error, then you will know that it no longer follows the even parity scheme. Thus, you know that there's some corruption in the data. Okay, so that is how you use the even parity scheme. There's also another way which is able to detect and also correct single bit errors. So just now here, if we only know that whether the data is corrupted or not, but we don't know which single bit is the one that causes corruption. So say for example here, it can be possible that this one bit is corrupted, or it can also be possible that another bit is also corrupted. So we don't know that which specific bit is corrupted. Thus, we introduce this thing called a 2D parity, which basically detects and corrects single bit errors. So how it does is basically if I have a data containing say 15 bits, then I will split them into 3 chunks of 5 bits each, something like this. So I'll be computing the parity for each row, and also I'll be computing the parity for each column. Okay. Then finally, this last corner here, the bottom right corner, this is basically just a parity bit of either the column parity or either the row parity or the column parity. So this corner here is just the parity bit of either the row parity or the column parity. So with 2D parity, we are actually able to detect 2-bit errors, and also we are able to detect and correct single-bit errors. Because now we know, for example, if there's a single-bit error, we can identify which specific row and which specific column, then we can just toggle that single bit. That is for single-bit errors. Okay, up to this point, any questions? Okay, if no questions, I'll move on. So there's actually 2 different parity schemes. One is if you want to make all the number of ones as an odd number, The other one is if you want to make all the number of ones as an even number. So in the lecture, we introduce an even parity scheme, but yeah, this one is just for additional knowledge. So there's also another scheme that we can use, which is called the cyclic redundancy check, or CRC. And if I remember correctly, this would be part of your third assignment later on. So this is part of your assignment 3. So in CRC, basically we both sender and receiver will have to agree upon something called the generator. So if your CRC will be of R bits, then the generator should be R plus 1 bits. Or rather, if you know the generator, then you can determine what is the number of bits in your CRC checksum, which is just the number of bits in the generator minus 1. Then you will get how many bits in the CRC. Okay, so these are some notation. We denote R as how many bits of the CRC checksum that we want. D is basically the initial data, and G is the generator that has been agreed upon. So to compute the CRC on the sender side, here's what we are going to do. First one is we are going to, wait. Okay, my PowerPoint is corrupted. Yeah, but anyways, so yeah, first method is basically we want to append R zeros to our data. So what do we mean by R zeros here? That is basically if your generator is 4 bits, then you have to append 3 bits of zeros to the end. Okay, so we append the number of bits in the generator minus 1. That's basically the first step. Then once we are done, we are going to execute something similar to long division. But instead of doing subtraction, as we usually do for long division, we are actually going to do it by the XOR method. Okay, so we are going to XOR it. So in this case, say 1011. If I XOR with 1001, then this will give me, this is 10, because this one is 0, this one is 0, this is 1, this is 0. Okay, so then I can put 1 in the quotient if I do an XOR at this certain bit. Then the next step is similar to long division. I'm going to pull these 2 bits down. So this will be 1010. Then since when I pull this bit, if I pull this one, I cannot do a long division with just 3 bits, right? So then I'll put a 0 here and I'll carry another bit down. So now I'll have 1010, so that I can do a XOR with 4 bits. So with that case, then I do another XOR. This will be 11, continuing all the way until we receive this remainder. So it is important to note here that actually for CRC, the quotient does not matter, but rather what we are concerned more is actually just the remainder. So the remainder here, your 011, is basically what is the CRC value. So I hope that from this example, you will notice that when you do division by binary values, right, then you will see that if your generator has 4 bits, then automatically the remainder here would be just 3 bits. So the remainder is always the number of bits in the generator minus 1. Okay, so that is the sender side of CRC. Now, what about in the receiver side? In the receiver side, instead of appending R zeros to the data, what we are going to do is to just append the CRC directly to the data. So this is the data here. The green one is the data. So I can just append the CRC value directly. Then I repeat the same process. So I'm just reversing it. But the way to check if there is corruption or not is basically by checking the remainder. If the remainder is everything 0, then I know that there's no bit error. Or rather, if the remainder is not 0, then there is bit error. Okay, so that is how we check for CRC receiver. So sender is you append zeros, get the remainder. Receiver is you append the remainder, check if the remainder is 0. Okay, if it's not 0, then there's a bit error. Any questions? No? Okay. So then we now discuss about the different protocols in the link layer. So I think last Friday, I actually came to the lecture. So I'm happy that I saw some of y'all have been attending the lectures also. But for those who probably haven't catch up, this is just a very quick review on what has been discussed. So yeah, these are the multiple access protocols in the link layer. So because the link layer is basically using something we call a shared link. Okay, so this shared link means that there might be a possibility that multiple nodes can send simultaneously using one single link or one single broadcast channel. So then we have to determine protocols to ensure like the data can arrive or to actually minimize collisions. Okay, so there are three main classes of link layer protocols, which is basically from channel partitioning, taking turns, and also random access. So let me just launch the next quick poll here. Among these three methods in the networking context, which is the most complex? Yeah, maybe you can answer to the Zoom poll. See, 5 people have been answering. Okay. 10 people have answered, maybe another 10 seconds. Okay. So 6 people answered channel partitioning, then 5 people answered random access. So I think these two are the more popular answers. So yeah, in the context of networking, okay, maybe in the context of a human behavior first. Channel partitioning means that if you want to talk, there are certain rules that you have to abide. Okay, so this one is kind of rule-based. Whereas for random access, this one is whenever you want to talk, you just talk. Okay, so this one is just yeah, randomly talk, similar to that. So of course, in the context of human behavior, then channel partitioning is quite difficult because you have to set multiple rules. However, in the context of networking, the more rules you have, the more orderly manner that everything will be conducted. So in case of channel partitioning, you will see that this one has no chances of collision, because when you want to speak or when you want to transmit a message, you can only transmit it within the allocated time frame to you. Whereas for random access, you can talk to it anytime. Thus, this one is higher chances of collision. And in cases of networking, what happens is we have to determine different types of protocols in order to just handle this collision. So in fact, with greater freedom comes greater responsibility, in a sense. Yeah. So this random access is actually the hardest to implement correctly in terms of a networking context, because you have to set the probability. You have to also ensure that the collision is minimal, while also to ensure what happens if a collision occurs, how do you actually recover from that. Thus, this one is actually more complex compared to just simply channel partitioning. All you need to do is to just set certain time frames, and yeah, everyone can just send at that point. Okay, so that is just, yeah, this is kind of the opposite of human behavior lah. So let's try to see what these classes are. First one, channel partitioning, means that the channel are basically allocated into multiple pieces. Thus, every node will have their own allocated piece. So there are two types of channel partitioning here. First one is your TDMA, which is time division multiple access. Means that, say for example, I have a time frame. Every single 10 seconds, one single node can transmit at that point. But if it is not your time frame, if it's not your round or your slot, then you cannot send. So in the case that, say, if 10 people want to speak, this is similar to me saying, okay, say Jason can only speak for 10 seconds. Afterwards, Yi will have to speak for 10 seconds, then Chen Xin 10 seconds, then go back to Jason. So suppose that Jason wants to speak, but Yi and Chen Xin doesn't want to speak. He will have to wait another 20 seconds before he gets his slot again, right? So then unused slots will go idle. Thus, this is actually inefficient. Okay. The way we compute efficiency is basically, say if you have n nodes, if only one node want to transmit, logically speaking, this node has to have the full bandwidth, as in there should not be anything that's limiting this node to transmit whenever it wants. Okay, so that is the first type of channel partitioning. There's also another type of partitioning, which is your FDMA, frequency division multiple access. This is similar to saying, say, for example, if I send a cable, they have multiple frequency, right? The lower frequency one, the higher frequency one. So each node can send at a specific frequency only. So that is just the frequency division multiple access. Okay. Any questions so far? No questions, okay. Then the next one is actually taking turns. So taking turns, we can also take a human behavior version is like similar to you have a seminar. Now say for example, I am the moderator and all of you here are the panelists. So if I want to give you a chance to speak, then I will have to come to you, I give you the mic, you speak. Once you are done, then I pull the mic over, then I give to someone else, then the person can speak. Okay, so if this person doesn't want to speak, then technically he can just return me the mic. I'll pass it again to another person. Okay, so this is what we call polling. There's basically one person called the master node. This is like the moderator. This person will control when other nodes will transmit. So in the case that one node is very talkative, too many speaking, right? Then you can just like, okay, stop within a certain time limit, 10 seconds. Then you take back, you give to another person. So in the sense that polling is much more efficient compared to, this is much more efficient compared to the previous one, which is channel partitioning. However, there is still some overhead for polling because there is some time taken when you take the mic, give it to another person before the person returns you the mic. Okay, so because the master node has to poll each certain node, there's going to be some overhead. Plus, if the master node fails, like for example, if you have a seminar but your moderator dies in the middle or has a heart attack, then that is what we call the single point of failure. Okay, so another way that we can handle this is also by something called token passing. So token passing is the case where instead of having a moderator, the panelist will be just acting as the moderator. So it will take the mic, speak. Then if he doesn't want to speak, then can just pass to another person directly. So each node will serve as the mic holder, like in a sense. So the control token or the microphone is being sent sequentially among the nodes, where while there's some overhead because of propagation delay and also because you have to process something, and token is also a single point of failure here. Because if the token is lost or corrupted, then that's gone. You cannot communicate anymore. Okay, so there is token passing. Now, finally, we have the random access. Random access is where you can just talk anytime you want. So in that case, then you have a probability of collision. Collision happens where two or more nodes are transmitting. So there are three types of protocols that we discussed in the lecture. First one is what we call the slotted aloha. So slotted aloha happens when you divide the time into slots of equal length, and we assume each frame are of equal size. So at the start, say for example, three nodes want to transmit. They can just transmit at any point in time. So here, all three transmit, but it's collision. Thus, they will have to wait. Then they retransmit with a certain probability t until the transmission is successful. Okay, so now when the subsequent frames come, they can retransmit under a certain probability. Okay, so that is a slotted aloha. Another version is what we call the pure aloha or aloha without slots. But of course, this will incur actually a lower efficiency because, say for example, if I send this one frame, then there's a higher probability of overlap because one node can send at this point or the other node can also send at this point, then this will result in collision. Just one bit collision will already incur as a collision already. Okay, so that is a pure aloha. This will actually reduce your efficiency. Okay, then of course, another way that we can see this is what if you wait first, see if anyone is speaking. If no one is speaking, then you speak. That is what we call the carrier sense multiple access. So we kind of sense the channel before the transmission. If no one is speaking, we transmit. If someone is speaking, then we wait for a while. Of course, there's still a chance that collision can occur. This is because, say, for example, in the context of Zoom, okay, when we talk here, there's going to be some form of delay or lagging, right? For example, like a 500 ms delay. So say two people want to speak. One is like, say, this is Abi want to speak in Zoom. Then another one say Yiming wants to speak in Zoom also. At the same point in time, they sense that no one is speaking on Zoom. So then they try to speak. But because of this delay, it can only arrive to the other person after 500 ms. So it's possible that after 500 ms, these two will actually collide. It will be like multiple voices together because of a certain delay. So yes, collision can still happen. It's because of propagation delay. Thus, when collision happens, that's where we have to update the algorithm, or rather we update the protocol to actually include the CD, which is to detect collision. What happens here is basically you just stop the transmission once collision is detected. Then at a random amount of time, you will retransmit. Similar to this, pure CSMA will not stop after collision. So this will just continue all the way. Whereas CSMA CD is like more rational. It's more of it's a good citizen. So when you listen to a collision, then you just stop there. Okay, so that is CSMA CD. Then you will retransmit at say some random amount of time. Okay, so this is CSMA CD. Then because that there is possibility that say for example, if I only send 1 bit, this is only 1 bit, then another person also send 1 bit, it's possible that it can collide in the middle, but you will not detect a collision. So this will actually come down to how a person or a node detects collision. Collision can only be detected if you receive any amount of data while you are transmitting. If you're no longer transmitting, then you will not be able to detect collision. Okay, that's why we have to set some kind of a minimum frame size such that this will help to counter the case of propagation delay. So we kind of want the minimum frame size to be at least the propagation delay. So in Ethernet, the minimum frame size is going to be 64 bytes in this case. Then also there's something called the exponential backoff. So exponential backoff is the case where CSME CD will actually propose some kind of a smart algorithm in order to determine how random it is to continue transmission. So it is basically setting a certain range, say 0, 1, all the way to 2 raised to n minus 1. This n depends on what is the number of collisions that has happened. So in the case where n is equal to 1, so it's like the first collision, then you can just randomly choose between either you transmit directly or you wait for like 1 times 512 bit times. If it goes to 2, then you multiply the range by 2 all the way until you reach the maximum amount, which is at 10th collision. So when n reaches 10, it will stop increasing the range. So then the highest amount that you can wait is just 1023 times 512 bit times. That's the highest amount that you can wait. Now, the lecture also mentions that if it exceeds 16 collisions, then you will just cancel the transmission at all. Okay? Yeah. So any questions thus far? This is, I think, the last slide of the recap. It's a long recap today. Any questions? Okay, if no questions, now let's move on to tutorial questions. So if you want to answer, you can just feel free to raise your hand on Zoom, or you can just enter your answers in chat. Yeah, I think chat is also better. Okay, so first question. Suppose that all links on the internet, if all of them are to provide reliable delivery service, so all the physical links, they are reliable, would the TCP reliable delivery service be redundant? Basically, if we say that, say suppose the link layer is reliable, do we still need TCP or not? Given that the condition of reliability is that every packet will always come. This is the link layer condition. What do you think? Do we still need TCP in this case? Okay, one person answered in chat. Maybe you can send in the public message also instead of a DM. Okay, so Galen mentioned here that reliability does not imply efficiency or error-free. In a sense, TCP also does not provide efficiency, but yes, the error-free side is actually true because here, if the concept of reliability on link layer is just like whether it arrives or not, then it might be possible that you have collisions, right? So then error-free is not guaranteed here. Anything else? Thank you, Galen. Okay, so let's see. There's actually a main condition that we have to see. Suppose that this host wants to send two packets, exactly as what Jason mentioned here. Say 2 packets, they are being sent. But because the network itself, we know that packet switching is actually, it might not always go through the same route. It depends on whichever route has less congestion at that point. So this can actually go through different routes. So when it goes through different routes, you will see that when it arrives at the destination, the packets can go through different links. Thus, it doesn't guarantee that packet reordering won't happen. So there has to be one certain form of protocol that can help you to reorder things. Thus, that is when TCP will be needed to actually sort the received data in the correct order. Yeah, so that is one case. Another case is also, of course, if they provide reliable delivery service, there would have to be one point where if something breaks, okay, that will also be a consideration, because now we are talking about physical items, right? So there can be possibility that it also breaks. Thus, we still need some form of reliability in terms of the software. Yeah, that is just one point that we can discuss. Any questions for question one? Nope. Okay. So then question two. So in question two, consider a 4-bit generator with value 1001. What is the CRC checksum R if data D has the following value? Has anyone computed this? Maybe can share in chat. Yeah. Also, if the others, if you see that any message has been sent in chat, you can also just feel free to send another one, or you can give a reaction if you agree. Oops. Anyone computed this? 110. Okay, Rachel said 110. Yeah, if you agree, can add a reaction to her message. If not, can also can also just give another answer. Yeah, I think I'll export the chat log for participation also. Okay. Okay, so yeah, the answer is 110, that's correct. I think y'all are the lucky people. Last year when I conducted this tutorial, I actually asked 4 people to come up and then they share their method. Okay, but for question 2A, this is how you're going to do. Same thing with the CRC sender. First step is you are going to try to append the number of zeros. Since here the generator is 4 bits, so the number of zeros we have to append is just 4 minus 1, which is 3 bits. Okay, so that's the first step. Then we do the long division by using XOR. So here we put 1001, XOR this, we get 101. Pull the next bit, XOR, pull the next 2 bits, XOR, all the way until we reach the end. That is, we get 110. Okay, so this is the method to compute the CRC checksum. Any questions for this? Yeah, note that we don't care about the quotient here, so it's fine to omit this, unless the question says that you have to include the quotient. Okay, so with the same thing, we can apply to the second question, which gives us 011. Third question gives us 011 also. And finally, 2D, it gives us 110. Okay, so that is for question 2. Now let's move on to question 3. So question 3 is actually talking about the checksum and the 2D parity check. So suppose that we have this 2D parity matrix. We want to compute the row sums, column sums, and also the parity bit. So how do we do this? By the lecture, we learned that all this will be done through the even parity scheme. So if the data contains an odd number of ones, then we add 1. If it contains an even number of ones, then we just add 0. Okay, so let's check the row. Here, the first row, 0, 1, 0, 1. This is already even, so we put 0. This is also even. So all the row parity will be 0 here. Column parity 0, 0, 0, 0 gives us the corner value. Corner value, we see that on the column, on this row parity column, all of them are zeros, so there is 0 ones. Thus, this is even already, so we don't need to do anything. So we just put 0. Or you can also check through the row of the column parities here. This one also contains an even number of ones, so we just put 0 at the last corner. Okay, so that is how we compute the row sum and the column sum and also the final parity bit. Any questions? No? Okay. So I think there was this one question on my tutorial yesterday. So the question was like this. This parity bit is going to take the even parity of either this column or this row. But the question is, will these two always have the same parity? What do you think? Yes. One person said yes. Others? Yes, yes. Okay, why yes? That's the main question. Why is it yes? Okay, so this is how you can think of it, right? Suppose start with all zeros. Say if I have just this data, then I can compute the row sum, the column sum. This will be 0, 0, 0, 0, 0, 0, 0, then the parity bit will be 0. Okay, this is just if I have data which is all zeros. Now, let me just change one of the items. Say if this changes to 1. If this changes to 1, then the row sum will be updated. Column sum will also be updated. Now both of these are going to be odd. Okay, if I change another data, say if I change this to be 1, then it will also update this thing. This will now be even. This will now be even also. So you will see that every single bit that I change, this will toggle out the row sum as well as the column sum. Thus, it will switch alternately between odd and even. Okay, so both of them will have the same parity. That's a simple way of proving this. Okay. Yeah, so now for question 3, we want to see how we can actually detect and correct errors. So for 3B, we want to see how do we detect 1-bit errors. Say, for example, if one of them is erroneous, if I flip one arbitrary bit here, then I can check each of the row sum and the column sum. Now I check here, I see that, oh, the row sum, it detects that there's an error because now these have an odd number of ones, but the parity bit is 0. So this is an error here. When I do the column sum also, I detect that there's an error in this column. So I know exactly which row, which column I need to fix. Thus, I can just flip this bit back to 0. Okay, so that's how you detect and correct 1-bit errors. Now, what about 2-bit errors? So this one, you can just arbitrarily choose any 2 bits. So for example, I choose 2 bits here. Say these 2 bits I change. Now, if I do the row sum will tell me that the first row is erroneous because these are 3 odd ones, but this one is 0. This one 3 odd ones, this one is 0. But now let's try to take a look at the column sum. If I do the column sum, this is 0, 1, 0, 1, even, this one is correct. 1, 0, 1, 0, even, so correct. 1, 1, 1, 1, this is even, so this is correct. 0, 1, 0, 1, 0, this is even, so this is correct. Now, based on this condition, you will see that the column sum detects nothing is wrong. Yes. So thus, in this case, we know that 2 rows are broken, but we don't know which column is broken. So in that case, we cannot correct 2-bit errors. Okay, any questions thus far? Okay, now let's go to question 3D. Now we want to give an example of a 4-bit error that cannot be detected. Anyone has an answer to this? 4-bit errors that you cannot detect. No one? Okay. So this one actually, if you choose any 4 bits that is located in like a square position, say for example, if I choose this, maybe this and this, if it forms like kind of a rectangle, then actually it will work. Yeah. So in this case, let me choose these 4 bits. Say for example, these 2 rows and 2 columns. Now we will see that if we compute the row sum here, this one is correct. This one is correct. So any row sum is actually correct here. Column sum also looks okay. So this is exactly the case where you cannot detect. Okay, so that is what happens if it's 4 bits. Yeah, so then you will know that for 2D parity check, there's actually a way to bypass this. Yeah, so that comes to the question of if 2D parity check has its weakness, right? Why do we want to use 2D parity check instead of 1D? The answer is actually coming down to a probability theory. Because the way that 2D parity check fails is if you have coincidentally a 4-bit errors where it's located in a square or a rectangle manner, right? So then you count the probability of how do you actually get that 4 bits. Compared to if you do 1D checksum, any 2 bits you flip, likely that is going to be undetected already. So there's a lower chance of detection error when you do 2D parity. That's basically the trade-off that we have. Okay. Any questions for question 3? If not, then we move on to question 4. So for question 4, suppose that we have many nodes in a shared medium framework, and then most of nodes are likely to transmit frequently. So the question is, which of the following multiple access protocols are suitable? So in this case, let me just launch one final poll. This one is a multiple response poll, so feel free to choose any options you like. It's multiple response. 。 . 。 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 。 . 。
。 . 。 . 。 . 。 .
Yeah, so the key word here is actually, you need to note that it says many nodes, then it says that likely they are to transmit frequently. Okay, I see 10 answers. Let me wait for another 10 seconds. Okay, so a majority says token passing, 8 people says TDMA, 3 people say CSMA. Okay, so yeah, I think the two majority answers are correct. So the answer here would be actually both TDMA and token passing are suitable. So to imagine this, right? Imagine that you will have, say, 100 aunties, 100 Singaporean aunties, you place them together in one room. Okay. If we assume that, say, for example, each auntie has something to bring, something to talk to, right? Then we assume that all of them are going to transmit frequently. Now, the question is which protocol is suitable for you to actually understand every single auntie there. Yeah. TDMA means every single auntie you give them 10 seconds. Then in that way, there should not be any collision, right? Then is it efficient or not? If you assume that every single person will likely to transmit frequently, then the likely the efficiency will actually be quite high because every nodes want to transmit items, right? So if TDMA is suitable, then token passing is also suitable because this one is just more efficient than TDMA, right? Now, how about CSMA? CSMA is not suitable because of the quantity and also the frequency. You have many nodes, all of them are likely to transmit, then you have a high chance of collision. 100 aunties together, all of them speak at the same time, all of them bake off at the same time, then all of them speak again. You will never listen to anything. Okay, so that is exactly CSMA. Any questions? Yeah, this is why when it's a large group of people, you likely will need someone to actually moderate them, right? So that's when TDMA and token passing is helpful. Okay, so that's question 4. Now we move on to the last question. So the last question is about CSMA CD. So we assume that two nodes are accessing a shared medium using this protocol. Then we assume a propagation delay of 245 bit times, and the minimum frame size is set to 64 bytes. Suppose that node A begins transmitting at t equals 0. Before A finishes, B begins transmitting a frame. Now the question that lies is actually when is the latest time that B can begin transmission. So in this case, we have to first analyze this question can actually be rephrased as this thing. When is the latest time that B can begin transmission is rather like you can say it as when is the first time that B can no longer transmit. So that moment actually comes when the first bit of A will arrive at B. Because when A arrives at B, then at that point, B will sense that someone is speaking, so B can no longer speak. Okay, so here we see that this is A starting to transmit at t equals 0. At time t equals to 245, that's equal to the propagation delay. The first bit of A has already reached B. At this point, then you will now constantly receive data from A all the way until the minimum frame size is reached, right? So what is the last time that B can transmit? That is just exactly 1 bit time before A comes. So if A comes at t equals to 245, then the latest time that B can transmit is just 1 minus, subtract 1 from 245, that gives you 244 bit times. Okay, so that is the latest time that B can transmit. Whereas for the next question, suppose that B begins transmission at this time. If B begins at 244, our concern is whether A can detect that B has transmitted it before it finishes transmission. Okay, so this question can also be rephrased as such. When B's first bit comes to A, is A still transmitting or not? Okay, because the condition for detection is basically you have to receive data while you are transmitting. So we can try to analyze this. This is the transmission for A. A will begin transmission at t equals 0. Then we know that there's a minimum frame size of 64 bytes. Thus, it can end earliest at 512 because of 64 times 8. Okay, so this is the earliest it can end. Of course, it can end much later, but we concern with the edge case, which is what happens if you reach the minimum frame size. Then now we simulate the same thing with B. If B starts transmitting at 244, then the moment it reaches A, It's just the moment it starts transmitting, 244 plus the propagation delay, that is equal to 245. So 244 plus 245, that gives us 489 bit times. And we see that this number is still less than 512, which is the earliest last transmission time that A can have. So yes, A can still detect in this case. That's why we still need a minimum frame size. So if I consider like another question of what is the largest frame size such that A will not be able to detect, then I can just find what is the case where A will not be able to detect. So at this point, T equals to 488. Then I can divide by 8. I will get the answer to be just exactly 61 bytes. Yeah. So if it's 61 bytes, then A will not be able to detect. But if it's more than that, then it should be able to detect. Okay. Any questions for this point? Questions? No? Okay. If no questions, then that is it for this tutorial. In case that you haven't marked your attendance, please scan the QR code and fill in the Google form so it's easier for me to track. But other than that, then that should be it for today's tutorial. If you want to access via the computer also, can use that link in the chat. Okay. Yeah, so that's it for the tutorial. Thank you very much for coming. Happy long weekend. Hope you enjoy your well-being day. Please take care of yourselves, guys. Recording will be uploaded, yes, in the same YouTube playlist. Yeah, no worries. Okay. Yeah, if you have nothing else, feel free to leave, or if you have any questions, can ask here. I'll be able to entertain them. Thank you for coming, everyone.